All right, well, let's finish off this section on space coordinates and vectors in space. Okay, so this is interesting stuff. Okay, so remember we ended last time by looking at these 2 points in space as kind of forming the endpoints of a diameter of a sphere. Yes. And then we said, all right, so what is the equation of that sphere if indeed that segment that joins those 2 points forms the diameter of a sphere? Well, we said the center of that sphere would have to be the midpoint of those 2 things, yes? Would have to sit on the midpoint of the segment joining those 2 points. So we computed that. And then we said, what is the radius from the center, what is the radius of this sphere? Well, there's a couple of ways you could compute that. Either you could take the length of the segment and divide by 2, correct? Or, which is kind of what we did, or you could just compute the distance between the center and one of those 2 points. Yes? We have the center, and you compute the distance to one of these 2 points that are at the end of the diameter, and you'll have the radius. Okay. What's going on here? It's like, okay, yeah, because now COVID can go into your eyes, apparently. Okay, yeah. All right, so we just got to be extra cautious here. Okay, all right. So we got that the equation of the sphere is given by that, right? Remember, it's like x minus the x coordinate for the center squared plus y minus the y coordinate for the center squared plus z minus the z coordinate for the center squared equals the radius squared. That's where that equation came from, okay? We talked about why the equation of a sphere is directly connected to the distance formula, and we even looked at the distance formula in great detail to kind of sort out what was going on there, and there was a beautiful little interplay of like 3-dimensional right triangles, yes? Pythagorean theorem being applied twice. Okay, so here's a little rendering of everything in GeoGebra. Okay, so do you see this thing? So here are the 2 points we started with. There's 2, 4 minus 3, 6, 2 minus 1. Here's the midpoint. I even drew a segment on here. Now, you can be a complete idiot, and believe me, I am, with GeoGebra and still kind of sort out what to do, okay? You basically just start typing whatever you think you might want to use. So like in this case, I was like, I wonder if there's a segment function, okay? And like you write SEG, and then it like spits segment out. Do you see that? Again, it's not thinking, it's still a machine, right? I just want to make sure we're clear on that fact, okay? It's a machine, but it says segment what? What do you think of that? That's going to be segment point. Well, that's going to be a segment drawn between those 2 points, yes? And it will actually do that. So that's literally what I did on that thing, okay? And these points, all I did was just write parentheses 2, 4, 3, and then it automatically labeled everything for me. Of course, I had to tweak some colors and whatnot. There's some nice things you can do. For instance, if I select one of these, right, and I literally, all I did was just type in the equation of the sphere right here. If I wanted to change the color of stuff, I could do that. Like I go here and say settings, okay, and it's like color, and I'm like, man, I like turquoise better, okay, and I want it to be really dark turquoise, which is just amazing, right? And it looks like that, right? See, and now that thing isn't even opaque at all. Opaque means that you can kind of see through it, right? So I can increase the opacity, I guess, however you say that, by, it is called opacity. Do you see that? That's amazing. And I can kind of decrease that a little bit, and then that thing won't be so obnoxiously see-throughable, right? Now I can actually see through this thing. So there's my sphere right there in the color cyan or cyan or whatever you call it, right? Turquoise color. Yeah? All right. So that's cool. GeoGebra is very flexible. It's a nice thing for sure. By the way, I think in here I can actually, I can do things like show the plane, like that's the XY plane right there. And look, that sphere kind of bumps up through the XY plane. You see that thing, right? But I could also show like, the other couple of planes that we were talking about last time. For instance, if I say X equals 0, that means Y and Z are free to do whatever they want. And I get that plane right there. Do you see that? And if I say Y equals 0, then X and Z are free to do whatever they want. And now I have like, you see that? You see the 8 boxes that are formed in space by these coordinate planes. Okay, the XY plane is the usual one that we've been working with so far. And then I have the YZ and XZ planes. And you can see the 8 octants. Yes. Here's the first one right here. Here's the second one over here. The third one is kind of over here. And the fourth one is right here. See what I mean? And then I would go below to see octants 5 through 8. Okay. I kind of lifted this thing up. I'm like, here's the 5th one. Here's the 6th one. Here's the 7th one. And here's the 8th one right here. Yeah. So that's kind of cool. You can see that pretty clearly 3-dimensionally. I think that's cool. All right. So there it is. There's our sphere. There's our coordinate planes. That's good stuff. All right. So let's move on and start talking a little bit about vectors. Okay. A vector, V, in standard position. In standard position, what that means is, right, standard position means that it comes out of the origin, right? So it emanates from the origin. Okay, so kind of writing a vector in standard position. Here's the component form of that thing. This guy would be the terminal point of the directed line segment. And of course, the initial point would be the origin, right? So initial point of the vector would be 0, 0, 0, okay? Yeah, okay. The 0 vector is still denoted by bold 0 or 0 with an arrow over it, okay? Okay, 0 like this, and it just gets an additional coordinate, okay? Standard unit vectors are I, J, right? So I still represents 1 unit of movement in the X direction and no movement elsewhere. J, 1 unit of movement in the Y direction, and K is 1 unit of movement in the Z direction. And of course, well, let me just say here, if V, let me just write this down right here. If V were equal to V1, V2, V3, written in component form, how could I write this in IJK form? What would be the way I would write this in IJK form? V1, I'll write it with a little hat like that, plus V2, J, plus V3, K, right? So that's kind of the way that physicists tend to gravitate towards the writing of a vector in component form. They tend to write it in IJK form. They tend to think of it as a combination of I, J, and K. Of course, 2 vectors are equal if and only if each one of their components are equal, yes? The X movement, the Y movement, and the Z movement all have to be the same. Hopefully that's clear. Does that make sense? Does this stuff all make sense so far? Okay, we're just transitioning from a 2-dimensional paradigm to a 3-dimensional one. Any questions on that? All right. if V is represented by the directed line segment from P to Q, right? So in other words, this is PQ with the arrow going like that. So that means we're going from P to Q, all right? I know, sometimes I get lazy and don't put like the bottom part of the arrow, but I mean, I think you get what I mean here. Right? I make like a little barbed arrow, okay? Well, I would have to figure out how much X movement occurred in going from P to Q. Well, that would be the difference between Q1 and P1, yes? Similarly, I would subtract the second coordinates from each other. I have to be very specific about the order in which I do this. I'm ending at Q, so that means I would take, Q2 minus P2 to see how much movement took place in moving from P to Q. Similarly, in the third coordinate, yeah? What about the length of a vector? Well, it's the Pythagorean theorem again, okay? It's just going to be the sum of the squares of the coordinates in the component form, okay? Square root of that to get the length. What about a unit vector in the direction of V? Well, it's no different than what we did in two-dimensional space. You simply divide the vector coordinate by coordinate by the length, yes? Or said another way, you multiply by 1 over the length of the vector. So if I had a length 50 vector before, then dividing each coordinate by 50 is going to shrink it by a factor of 50, and my new length will be 1, yeah? Okay. What about adding two vectors together? Well, again, that's sort of the resultant force. If these vectors are thought of as forces, this would be the resultant force of each two of those vectors. And we would get that by adding together the sum total forces in each component, yeah? In X and in Y and in Z. So we simply add things together coordinate-wise. By the way, we're going to have a lot more flexibility with our vectors coming up pretty soon. In the very next section, actually, we'll look at a kind of a vector product. We've already seen sums and differences of vectors, yes? And scaling of vectors by scalars or constants, yeah? What we're going to see next is, okay, are there ways I can multiply vectors in a meaningful way? And it turns out the answer is yes, there are two separate kinds of vector products that actually tell us a lot of information about the vectors. Okay? So here's a scalar times a vector. Of course, you just scale each one of the components by that same constant. And what do you think is true if I computed the length, okay? The length of CV. What do you think that's going to be? Think that's going to be any different than it was in two-dimensional space? No. It's going to just be the absolute value of C times the length of V. It's just going to scale the whole length by absolute value of C. I take absolute value because C could, in theory, be negative. Okay? And all other properties still hold that we had before, like the associative property of addition of vectors, the distributive property of, a vector over a sum of scalars, or a scalar over a sum of vectors. All of those properties we had in two-dimensional space still hold, okay? Any questions on this so far? It's pretty standard stuff, and it shouldn't be that surprising given what happened in two-dimensional space, okay? Let's do an example. Find the component form of and the length of a vector if its initial point is 117 and its terminal point is 2, 5, minus 3. Okay, so this is, I don't know, let's call this guy P and let's call this guy Q. So what we're saying here is that V is supposed to be the directed line segment from P to Q, right? Well, what we have to do is kind of subtract coordinate-wise in the appropriate order, the stuff from Q from the stuff from P. Okay, so it's going to be 2 minus 1 in the first coordinate, 5 minus 1 in the second coordinate. -3 minus 7 in the third coordinate. And we get 1, 4, -10. Yeah, 1, 4, -10 as the component form of that vector or of that directed line segment. Okay. And what about the magnitude? Well, that's easy. You just sum the squares of the components and take the square root. Yeah, so you get 1 squared plus 4 squared plus -10 squared. And by the way, please, 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 please make sure when you have a negative component that you square it so that the negative goes away. If I ever see you put a negative under the square root when you're trying to find the length of something, that is not good, okay? A lot of times people will sort of incorporate a negative in place of that plus sign right there. I don't know why that tends to happen, but please don't do that, okay? So I get the square root of 117 is the total length of this thing, yeah? So what do you think the next natural question is going to be? Look, I have the vector going from P to Q. I have its length. What if I want a unit vector in the direction of that thing? Well, that's easy enough to do. I just basically take the original vector v and divide by the length, divide coordinate-wise by the length, which is the same as scaling by 1 over the square root of 117. Okay, so I'm scaling that thing by 1 over the square root of 117, and of course, that effectively divides each coordinate by the square root of 117, the length of v, right? Does that make sense? Okay. So I want to go see this thing visually here, but yeah, hopefully that makes sense. I'm going to go over here and kind of see some of this stuff visually in GeoGebra. Now, look, I got to get rid of some of this junk, right? Just get rid of all this junk. Okay. Now, what were my points? Can someone read those off to me again? Oh, by the way, I don't like this. Well, actually, I'll leave that here. I'll leave the XY plane in there. Okay. What were my points again? 1, 117. And what was the terminal point? So do you see how it kind of puts that right there? Do you see that? Yeah, 117. By the way, if I wanted to label this thing, I can do it, right? So first of all, the color, I'm going to make it black, okay? So it stands out nice and, nicely. And then I show the label. I want to show the name and the value, okay, of this thing. Then it actually kind of labels the point. Do you see that? So 117, what was the other one? 2, 5, -3. All right. Okay. Okay, so there's that. Of course, I'm going to do the same thing to this one. Okay, name and value, color, black. Thank you very much. Yeah. Okay, so here we go. Oh, what in the world is going on here? What is up with that? Why is it not the right color? What is that? What's that little whale tail thing going on there? Okay. I don't know what's happening, but oh, now all of a sudden it decides to be black. Okay, so if I want the vector, what do you think I should type in here to kind of make the vector thing make an appearance? What do you think I should type? How about V, E, C, okay. Okay, so vector, okay, now it actually asks for a starting point and an ending point, yeah? Okay, so look, I can just put 117. Okay, and what about the ending point? That was 2, 5, -3. Okay, there it is. Do you see it? That's cool. There's this vector kind of pointing down in that direction. And of course, if I want to see that thing in standard position, I could pull that off, couldn't I? Yeah. By the way, I mean, if I really wanted to, I think I can click on these things and change stuff. So settings, maybe if I wanted to name it like P, yeah, so that it fits more with the problem that we were working on. And then I go down here and I say settings, change this to Q, yeah. Okay, so I have PQ now, so it looks a lot more like this. And this thing is called U. I don't like that. I'm going to call it, what was it called over in the other, or over on the slides? Like V or something, yeah. Okay. And there it is. Now, if I wanted to see this thing kind of from in standard position, I can pull that off by just saying vector. Now there's a vector where I just give a point. And if I just give a point, it will assume that's the terminal point and that the initial point is the origin, yeah? Okay, so vector point. So what is the point then? What would I put in here? Help me out here. I want to have the exact same vector drawn from standard position. What would I put as the terminal point of this thing? Yeah, 1, 4, -10, exactly right. Yeah, there it is. So there's this thing translated down into standard position. Okay, translated down into standard position right there. Yeah. It's the same vector, but it's just emanating from a different point. Make sense? Yeah, that's kind of neat. Moving on. Okay. Two non-zero vectors, u and v, are said to be parallel if there is some scalar such that u is equal to c times v. Okay. And the thinking here is, if I were to draw u and v in the same, or in standard position, and u is literally some scalar times v, then u and v would basically live in the same line. In the same line, they would be living in the same line. If I simply scale that thing, if I scale v by some kind of constant, then u and v will be living on the exact same line through the origin, if I draw these things emanating from the origin. Okay? So it is possible that two parallel vectors could be pointing in the opposite direction. Does that make sense? Like they could be pointing in the opposite direction. If the scalar is what? When would the vector get flipped around? If the scalar happens to be negative, yeah? If the scalar is positive, they will literally be pointing in the exact same direction, okay? They just will be different links potentially, okay? But parallel does include the possibility that the vectors point opposite to one another, yeah? But they would still live in the same line, yeah? Yes.
So why do they live in the same line, not the same plane? So like parallel lines are lines that are like they're parallel within a plane together. They're not necessarily in a line together. But you're saying that the parallel vector.
Well, but a parallel lines don't just live in the same plane, because I can think of lots of lines that live in the XY plane that aren't parallel. So that's not the only thing that characterizes them. Parallel lines mean that they have the same direction, basically. And you can almost imagine putting a vector inside of two parallel lines in the XY plane, and those vectors would be parallel. Does that make sense? And parallelism, the essence of it is captured in kind of a scalar, taking scalar multiples of a given vector. That's what's going on. And if you, right, so Daniel, if you took two parallel lines in the plane and you shifted them so that they're both going through the origin, what would happen? They'd be the same line, yeah? So that's kind of the essence of parallelism. If I kind of shift the vectors back to the origin, even if they're pointing in the opposite direction, they live in the exact same line. So that's the essence of parallelism, okay? So hang on, before I get into that last thing right here, I wanted to go back over here, sorry, okay? And I wanted to, let me see here. I wanted to take this vector u and get the length 1 version of it. Okay, so I think, what would I have to do? What did I have to do to this vector to turn it into the length 1 version of it? Yeah, 1 divided by the square root, okay? Square root of 117. Okay. Let me move this down a little bit so that you can see it. That is not what I was not done. Okay. 1 over square root of 117. I think, if I recall, that I can just put, well, it's not going to let me do that. So can I just put u right here? Yeah. Did it graph that thing or no? Where is it? Is it in here? Well, I probably need to say, no, I don't know. So let me see. Let me just get rid of this equal sign right here. It did put this thing in here, but then it didn't graph it. Oh, maybe I just need to go like that. Is it in here now? Where is it? Yeah, I think you're right. I think that is what's happening. It's hiding in there, but I can't really see. So what happens if I get rid of this? Oh, it is hiding. It's right there. It's just teensy. You see that thing? Good grief. That thing is like teensy, right? It's just barely kind of coming out of the origin. Yeah. And I could pick other multiples of u. For instance, I could take, let's do, 1/2. Let's say, suppose I went 1/2 times u. Okay. Do you see that thing right there? That actually produced something that's interesting. Okay. So that's another vector, w right there. And what if I flip it in the opposite direction? So like -1/2. Oops, -1/2 u. See how it points that in the opposite direction? But what's true about all of those vectors? They all live in the same line, right? I can kind of go like that and see that they live in the same exact line. Now, when we start describing lines in three-dimensional space, this fact is going to become exceedingly important, okay? This idea of parallel vectors, and vectors being the thing that really are at the essence of what it means for a line to have a direction of some kind. We used to call that direction the slope of a line in two-dimensional space. But hidden underneath the surface, the slope really was a vector. It was a vector of some kind, yeah? We'll talk about that later. Okay, so back here. Okay, here we go. So two vectors are parallel if one is a scalar multiple of another. So z is a vector that has initial point 1, -1, 3, and terminal point -2, 3, 5. Okay. And then I give you a couple of vectors written in IJK form. Now, by the way, notice u doesn't have an I in it, does it? So what does that mean the coordinate for x is for the vector u? 0. There's no movement in the x direction. There's 4 units of movement in the y direction and 2 in the z direction, but none in the x direction. Okay? So are those two vectors parallel to this vector z? Well, the first thing we would have to do is actually figure out what z is, correct? I gave you the initial and the terminal point from which we can actually figure out what z is. Okay? So do you guys believe me if I say z is -3, 4, 2? How did I get that? How did I get -3 for the x coordinate? How did I get -3 for the x coordinate? -2 minus 1. How did I get 4 for the y coordinate? What did I do to get 4 for the y coordinate? 3 minus -1, yeah? 3 minus -1. And how did I get 2 for the z coordinate? 5 minus 3. That's the sum total movement in the z direction. I went from 3 to 5, which is a total of 2 units of movement in the z direction. So my vector is -3, 4, 2. Now let me ask you, is z parallel to either v or u? And remember, that would mean that one of them is a scalar multiple of the other, yes? Is v a scalar multiple of z, for instance? Do you see something I can multiply z by to get v? 2. Which means actually v is twice as long as z, right? V is twice as long as z. Okay? Since v is equal to 2z, v is parallel to z. Now, what about that other thing? Is there any way that z could be parallel to u? No, why not? Does z have movement in the x direction? Yes. Does u have movement in the x direction? No. So there's no way that these things are going to behave like one another as far as parallels go. I mean, you would have to like, you know, if I was going to turn z into u, I would have to multiply by 0, correct? To kind of make the x coordinates match up. But if I do that, it's going to blitz the whole vector, yeah? If I multiply by the scalar 0, it would make all the components 0, which is no good. Okay, there's no such z such that c times z is equal to u. So u and z are not parallel. Based on the I components, c would have to be 0, but 0 times z is 0. 0 vector, which is clearly not what u is. Yeah? So there's no way to turn z into u via a scalar multiple. Okay, so they are not parallel. Does that make sense? Hopefully. Okay, so any questions on that? Just the idea of parallelism kind of playing itself out. All right. Let's talk about collinear points. Collinear. Points are, and I'm talking about literal points in space, okay? Points are collinear if they live on the same line. There's one line that goes through them all, yeah? Okay, otherwise they are not collinear. By the way, I mean, I could have said that in two-dimensional space also. I would have said, you know, if you give me 3 points in two-dimensional space, I would call them collinear if they sat on the same line. Okay, not every collection of 3 points is going to be collinear. Yeah? So here's a question. Are the points P, Q, and R collinear? How do you think we could tell if 3 points are collinear? What do you guys think? How do you think we could tell if 3 points are collinear? What do you think? Say that again, Kira? They wouldn't have to have the same x, y, and z values to be collinear. Collinear just means the 3 points live on the same line. So x, y's, and z's could all change. But how could I use vectors to tell me that these 3 points sit on the same line? Yes. Yeah, that actually is true. So, you know, there's something that I can like, yeah. But what does that have to do with like, how could I? Yes, right. And you could kind of do that separately for X, Y, and Z. But is there a quick way I could kind of sort out whether these are collinear just by looking at some vectors I might form from these points? Yeah.
If you connected 2 points,
Uh-huh.
the third point you have to line up. There's 2 points in one situation, so there's one situation where that doesn't line up.
Yeah, that's right. So like, I don't know, if this is P and this is Q and this is R, one way I could tell whether they're collinear or not is, I don't know, maybe I could think about drawing the vector from Q to P and the vector from Q to R. And what would have to happen if indeed these things were, what would have to happen if these 3 points were indeed on the same line? What would have to happen to the vector QP and the vector QR? What would have to be true about these things if these points were on the same line? They would have to be parallel vectors. There would have to be something I can multiply the one vector by to get the other one. Yeah? Okay, I have a little picture in here to show that that's what's happened. The answer will be yes if QP and QR are parallel. Okay, so if QP and QR, the two directed line segments, are not collinear, then there would be no way to multiply one of those vectors by a scalar and get the other one. Here, I mean, the picture is a little muddled, but Q is supposed to be right there in the middle somewhere. The other option is like, it could go Q to P and Q to R like this, yes? I mean, Q could be on one of the ends of this thing. But either way, you would have parallelism would tell us what was going on, okay? So what's QP? Well, I would have to, now P is the terminal point of these three things. So you would have to go 4 minus -2, which is 6, yeah? You would have to go -2 minus 0, which is -2. And you would have to go 7 minus 3, which is 4, okay? And for QR, you go 7 minus -2, which is 9. You go -3 minus 0, which is -3, and you go 9 minus 3, which is 6. Are those two vectors parallel? Is there something I can multiply one by to get the other? Is there something I can multiply this guy by? Is there something I can multiply QP by to get QR? 3/2. Does that work in every coordinate? Better if these are indeed parallel. Yeah, it does. 3/2 times each one of those coordinates gives me the other one. Yeah? Yeah. So since QP times 3/2 is equal to QR, the points are indeed collinear because these two vectors we formed happen to be parallel to each other. It's that simple. That's how we can tell if 3 points happen to be collinear. Okay? Any questions on that? Well, that's it. So get ready. Get ready for a quiz.